Good afternoon, everyone, again, and welcome to Public Health Ontario's Rounds presentation on Part 2 of AI Technologies in Public Health. Part 1 was earlier this month, and thanks to those who joined us then. Part 2 will focus on lessons learned from developing the automated opioid news event-based surveillance tool. We'll call that AONES. My name is Andre Villegas, and I'm a Senior Manager in Laboratory Information and Operations Support at Public Health Ontario, and I have the pleasure of moderating today's sessions. Before we begin, a few housekeeping items. The chat pod has been disabled to limit distractions during the presentation. If you have any questions during this session, please use the Q&A pod. And the Q&A session will follow the presentation. If at any point during this session you experience any technical issues, please email capacitybuilding@ohvp.ca. I'm obligated to state that as the moderator for this session, I have no conflicts of interest. It is now my pleasure to introduce the speakers for today's presentation, Alison Meyer and Alex Hamilton. Alison has a master's in public health from Queen's University. She is a research associate for KFLNA Public Health and is a data scientist associated with the Acute Care Enhanced Surveillance Program, or ACES. She has over 10 years of experience working in public health surveillance and program evaluation. Alison is passionate about data visualization techniques to improve reporting of public health surveillance. Alex Hamilton is a research associate at KFLNA Public Health with experience in nursing and biomedical informatics. He has more than 5 years of experience building machine learning algorithms for medical applications, including developing models for detecting prostate cancer and atrial fibrillation. At KFLNA Public Health, he leads algorithm development for ACES and AONES. He is passionate about blending technical and clinical expertise to improve healthcare outcomes and public health innovation. Welcome, Alison and Alex and everyone. Let me pass it now to Alison to start us off.
Thank you, Andre, and thank you all for coming today. Earlier in the month, we officially launched the Automated Opioid News Event-Based Surveillance System, or AONES, during the PHO Rounds. This tool was built through a locally driven collaborative project funded by Public Health Ontario over the past year. Today, we are here to share the lessons we learned during this project about undertaking applied AI projects in public health settings. Before we begin, I would first like to start with a land acknowledgement. We, here in KFLNA, live, work, and play on the traditional lands of the Haudenosaunee, Huron-Wendat, Mississauga, and Anishinaabe nations. In today's meeting, we have representatives from across Ontario, and so I would like to ask you to take a moment to reflect on the Indigenous nations whose traditional land you are currently on. In our reflections, we thank them for the care of the land from time immemorial, consider the impact of settlers, and reflect on how we can personally and professionally work to implement the recommendations of the Truth and Reconciliation Commission in our communities and across the country. But before we begin, a disclaimer on behalf of Public Health Ontario, who's hosting this webinar. This presentation was created by myself and my colleagues, but will be published on the PHO website as outlined in their terms of use. PHO is not the owner of this content, and any application or use of the information in this document is the responsibility of the user. PHO assumes no liability resulting from any such application or use. And also, I and my colleagues Nancy and Alex have no conflicts of interest to declare. There are 4 learning objectives to today's presentation. 1, describe the process of developing an AI tool for production. 2, identify common technical and human resource requirements for developing AI tools. 3, explain the iterative data exploration and annotation cycle. 4, plan for the knowledge exchange and technical production components to ensure tool use and sustainability. We will begin with a brief background of our project, then follow with the main topic, the workflow of an AI project, and the associated lessons learned for each stage. Following that, we will summarize some broad key takeaways and end with the question section. First, a brief background of the project. Given the content of today's presentation, we felt it was important to give a brief background to who we are and what our skill sets are. My name is Alison Meyer, and I'm a research associate at KFLNA Public Health. My undergraduate degree was in civil engineering, and then I did a master's of public health. While outside of a few courses, I have no technical training in computer science. I've been programming in various languages since I was a teenager, and I've worked summer jobs in data architecture teams. In my professional role at KFLNA Public Health, I am originally primarily a program evaluator responsible for both quantitative and qualitative projects. For the past several years, I have also been the data scientist working with Ontario's real-time syndromic surveillance system, ACES, and have been one of the organizational leads on developing internal and public dashboards.
Hello, my name is Alex Hamilton. I'm a registered nurse and a research associate here at KFLNA Public Health. I've been working in machine learning this space since about 2018, first on signal processing and then computer vision applications at Kingston Health Science Center and Queen's University, and more recently on natural language processing projects here at KFLNA for internal quality improvement activities and also for ACES.
Alex and I were the primary development team for this project. We are also presenting on behalf of our third colleague, Dr. Nancy Slitt, who is also a research associate at KFLNA Public Health and an adjunct professor in public health sciences at Queen's University. Furthermore, this project was a collaboration involving several other staff from our PHU, as well as 10 other PHUs, Queen's University, and the Ontario Drug Policy Research Network. The project included harm reduction staff and managers, epidemiologists and analysts, physicians, and policy specialists. We were also fortunate enough to collaborate with ODPRN's Lived Experience Advisory Group. Like our development process, Alex and I will be going back and forth throughout today's presentation. We wanted to begin with contextualizing a phrase we will be using a lot during this presentation: applied AI projects in public health settings. By applied, we mean projects that look to build tools that will be in production rather than used for one-off analyses. These tools are for ongoing use, and hence the data is evolving. We are also talking about tools where at least some of the development occurs in-house, not projects where you're purchasing software as a service that included AI within its development. By AI, we mean any range of AI and machine learning techniques, though for this project, we generally use natural language processing, NLP, related techniques. Public health settings. Small, service-oriented organizations, such as local public health units, though the lessons learned we share today would likely be applicable to other small health and other public sector organizations. Moving on to speaking about our project specifically, the drug poisoning crisis has worsened dramatically since the introduction of fentanyl in 2016 and was only exacerbated by the COVID-19 pandemic. Changes to the availability and types of opioids in the unregulated drug supply has resulted in an increase in substantial harms to persons and communities. The increasing risk resulted in an investment in surveillance systems to track the harms caused by opioids. Significant effort has been made by all involved parties to ensure timelier reporting, and these methods provide critical information for quantifying the impact of opioids in Ontario. However, there's still much they do not capture or do not capture fast enough to drive immediate public health action. Current surveillance systems are designed to capture the same type of information over time, which is important, but this rigidity decreases their flexibility and therefore their ability to adapt to changing human behaviors and changing outcomes. How can we help address this problem? By using large, non-traditional data sources and looking for unusual events, or a type of surveillance system called event-based surveillance. With these large data sources, we need different methods to extract and synthesize information, which provides an opportunity to use AI to aid in the automation of this task. This was the idea behind the AONES project. This grant-funded project was conducted from August 2023 to August 2024 and was designed with 4 objectives. 3 related to the development of the tool: develop and test data pipelines that take in and process new data feeds in real time, develop, train, evaluate, and deploy data pipelines, including AI components that filter articles and extract critical situational awareness information, and finally, build an interactive dashboard that synthesizes the extracted information. We presented on these first 3 project objectives in the first webinar. The 4th goal of the project took a broader, more evaluative view of the project as a whole and involved reflecting on the process we took in developing and deploying AI in an applied public health setting. We hope that by doing this, other similar projects and teams can learn from our findings, and this can support expansion of other projects like this in our settings. It is this objective that is the focus of today's presentation. To provide context for our discussion, we thought it would be helpful to quickly give an overview of our data pipeline. There is more detailed documentation on this on the website that hosts AONES, kfla5.ca.
So the first section of our data pipeline is where data is ingested from a service called GDELT. GDELT is a service that regularly scrapes thousands of media websites and uses a battery of machine learning models to extract details and append metadata to this content. So this is things like different tags and classifications of the material. We use two GDELT data sources in this project, the article list and ngrams dataset. The article list is precisely that. It's a listing of all the sources that are scraped by the service. The article list dataset includes URL, article title, and a short description when this is available. The ngrams dataset contains the same metadata plus additional rows of fragmented article text after the GDELT service performs a segmentation step. The first stage of this pipeline is the cleaning and harmonization of these two datasets. We then pruned the GDELT feed using rule-based natural language processing methods. And here we apply pattern matching in that metadata and the article fragments to reject articles that do not contain mentions of opioid or other drug-related terms that we deem to be in scope for this application. We then send the article list to a service called scrapingbee to obtain the full text of the original article. And parsing the raw HTML payload that's returned by this scraping service is conducted on AWS. We use Lambda functions in Docker containers. And we do this to protect the health unit infrastructure. We don't want to be parsing raw HTML from sites we're not familiar with. We then use vector similarity search and an annotated data set to propagate labels. And the labels here are whether the article is alert-based, crime-based, or other, to the full text payload that's returned from that scraping service. Articles that don't receive a label in this step are essentially pruned from the data set. Next, we pass the full text articles to OpenAI for information extraction. We do use a Python package called instructor to define and validate a data model and to exploit the function calling capabilities of GPT 3.5, with the data model in this case being drug-related details and geolocations that are scoped to the article level. Normalization then occurs, so to reduce the granularity of the extracted geocodes using Esri, the Esri web service. And higher tier geographies here are easier to visualize and bucket, and they do provide additional layers of privacy. Although the main reason here is because we're using this model, large language model, to do some inference about the geolocation. And finally, we load this data into a Postgres database, so a relational database system for visualization in Power BI.
Moving on to the main topic of today's presentation, the workflow of an AI project and the lessons we learned for each. We've broken the workflow into three major phases with two substeps each. The first phase is the background work needed before AI projects can start. This includes setting up the technical and organizational infrastructure and making plans for pipeline development and data storage. You then move into the cyclic development phase, where we want to share lessons learned about the understanding the data and iterating on ideas. The final phase is about actually using the project, where we will focus on data visualization and knowledge exchange and considerations for putting projects into production. Within each substep, we will be discussing the things we learned we needed to consider and account for, the types of decisions we had to make, and our processes. This will still be a very high-level discussion, as many of these stages could fill an hour presentation unto themselves. But before we get into the specifics, we felt there was one tension that influences all stages. AI projects are by nature experimental and explorative. While you may have a broad goal in mind for the end product, it is impossible to truly know where you are going to end up when you start. Both the components of the pipeline and what the end product is dependent on what models you test, what they can achieve, and the learning, exploring process from being embedded in the project. This is further exacerbated by the speed of development in the industry as a whole. Changes in the available technology can result in radical changes to your project at any point during its development. This absolutely happened to us. We had intended to develop in-house models for data extraction, but the rapid improvement of large language models over the course of the year of the project meant we completely pivoted to using these. We'll talk more about the specifics of this pivot and the considerations we took with it over the course of the following slides. It's just one example of the changes that can occur.
So one of the first orders of business for this project was to determine the storage and compute requirements for training and running task-specific supervised learning models in-house. Given the nature of supervised learning, we recognize the need for GPU-enabled hardware to handle both training and inference tasks efficiently. We also explored the possibility of deploying local large language models in concert with model as a service offerings like OpenAI. These tools would be used primarily for bootstrapping the annotation process in the beginning of the project, but we wanted to make sure that the hardware requirements were met for integrating local large language models as an end-to-end solution for data extraction if the feasibility, cost, and deployment considerations were determined to be reasonable. A significant challenge, though, was the time required to set up this local infrastructure. The process of procuring and configuring specialized GPU hardware was slow due to formal purchasing requirements in our agency, which led to significant delays in initiating our model development and evaluation. Further delays occurred once the hardware was actually acquired and on site, as it required collaboration with IT for configuration of user accounts, network access, server room co-location, and compliance with the various protocols in our agency, such as manage updates and disaster recovery. We also had to deploy a data orchestration tool called Dagster. This is the tool that we selected, and an enterprise object storage solution called MinIO. Deployment and testing of both of these services took several months, mainly due to the competing demands that are placed on our data integration team from other departments within the unit. Another challenge we encountered during the build phase was determining which parts of the application can and should be built internally and which parts could be offloaded to a service. Unfortunately, these decisions, for better or worse, are often decided less on their technical merit and more on funding arrangements and concern about the costs associated with maintaining data products long term. Like many public organizations, our agency tends to prefer capital expenditures over operating expenses. At KFL&A, capital investments are favorable because they allow us to build lasting assets that align with long-term objectives while also sidestepping some of the difficulties in securing ongoing operational funding in the budget environment typical to public health. Despite this reality, however, there are many situations where incurring an operational expense may be desirable or even necessary. This is especially true for ambitious data projects where the teams are small, timelines are short, and startup funding is comparably low or non-existent. Fortunately, though, from the generous funding from PHO, many of these decisions were actually much easier. For AONES, we tried to strike a healthy balance between capital expenditures and operation expenses. Ultimately, we decided to deploy foundational data infrastructure internally and offload activities of the pipeline that were too complex to external services. A good example of this is our selection of Scraping Bee, which is a high throughput external web service for web scraping that offers proxy rotation. Developing internal scraping infrastructure with the same performance and capabilities as Scraping Bee would have required significant development time and domain expertise. We also recognize that missteps during this building process could result in blocklisting of A1s and other agency assets on hundreds of news websites across the internet, which is obviously an outcome that was undesirable. So setting up the infrastructure for this project presented as many organizational hurdles as it did technical ones. One major hurdle in projects like this is navigating technology policies, especially around open source software. A1's, like many data science and machine learning projects, relies heavily on open source tools, but public sector organizations are often reluctant to support this software development or delivery model due to concerns about licensing, support, and compliance. So it's important to engage your IT team well in advance to starting a machine learning project. Approval of these tools often takes multiple rounds, and acquisition is likely to deviate from normal software procurement processes. So a good example of this in the Python ecosystem is downloading packages from public repositories. Data security is also critical, particularly when handing over potentially sensitive public health data if you're using a third-party service. Many service providers offer a specialized infrastructure for handling these type of data, but this usually comes at a huge cost, like enterprise licensing, for example, and attestations need to be made about other technical and administrative controls and safeguards to ensure that you actually are compliant. Finally, in small teams, especially within public health, there is a tendency to rely on generalists. And these are staff who wear multiple hats and shift between roles to meet project demands. This flexibility is invaluable, allowing a small, nimble team to handle a diverse range of tasks on projects that are like A1s. We are fortunate here at KFLNA to have a small team who are able to seamlessly blend data science, data engineering, and domain expertise in projects like these. However, I think it's important to state that there is value in having hyper-specialized folks on the team as well. Relying only on generalists can expose projects to risks in areas such as data security, some of your architectural decisions, and compliance, as one would imagine. Domains like these are where a fair amount of in-depth expertise is required. So without specialists to handle these areas, there is an increased risk of delays as well in your project, technical misalignment, and oversights really at the end of the day. We are grateful for the contributions of our data integration team who do possess many of these skills, and they spend countless hours reviewing and probing the foundational architecture powering A1s. So at its core, A1s is a data pipeline, a series of steps that involve data extraction, cleaning, transformation, prediction, and ultimately visualization in a dashboard. Orchestrating these stages effectively requires a tool like Dagster, which enables us to break down the pipeline into small, manageable steps. Each step functions as an independent unit of work that can be monitored, debugged, and re-executed without re-executing the entire process when failure occurs. This level of granularity is essential for efficient troubleshooting and optimization, particularly when you're working in a complex data flow. And an an added benefit of designing A1s this way was that we could actually program in automatic retries at specific steps. And this feature was particularly important because the project relies on external tools at various points in the pipeline that become temporarily unavailable when network or service fails. And this is something that did actually happen to us quite a bit internally at KFLNA. Unfortunately, the benefits of automation mostly come with a steep learning curve, particularly for data science teams that are used to writing one-off scripts. So be prepared for a deep dive into task partitioning, scheduling, and writing classes for custom resources and IO management. Deploying backend services also requires a significant amount of time and attention. Dagster in particular has a pile of dependencies, including its own database. In this case, we opted to use MariaDB, a daemon, and a web-based user interface where you can control some of the actions in your job. All of these different components need to be carefully configured. You can deploy them as containerized services with Docker, which for our team required additional learning and moderate amounts of pain. But these challenges aside, really, we firmly believe that these efforts have yielded a more structured, resilient, and scalable code base that will be more reliable and cheaper to run in the long term. This approach was a design choice, so all of this pain was something we inflicted on ourselves for a reason from the beginning, as our small team cannot dedicate a large amount of time to continuously monitor and maintain A1s without cost recovery. Another really important critical thing to consider here is data storage, not only for storing final outputs, but also for managing the intermediate assets that are generated at each stage of your data pipeline. After exploring several options, we selected MinIO as our object storage solution. MinIO enables us to store and manage huge volumes of data efficiently and provides essential features like site-to-site replication, which is good for disaster recovery and maintaining uptime, role-based access control and logging for security. So depending on your application, there may be some additional security and auditing requirements, and data lifecycle management. Lifecycle management here was particularly important to us because the data transformation pipelines generate heaps of intermediate data that can and should be purged fairly regularly. In MinIO, you can set lifecycle policies to automatically expire assets in specific buckets, meaning we can keep the runtime storage footprint for A1s very low without the need for constant oversight and intervention. And because MinIO is S3 compatible, so Amazon Web Service S3 compatible, we can also lift and shift the A1 storage layer to the cloud with minimal code changes if that becomes necessary. Our experimentation with cloud-native storage was dual purpose. First, it was to increase and preserve the scalability of AONES when and if we face storage pressures in our cluster. And second, to help our team become more familiar with these design principles and the interface as we modernize data infrastructure at KFL&A.
Moving from the background stages to the cyclic development stages, we first wanted to talk about the data itself. In our case, the data was full text, but I do feel the overarching lessons would apply to projects with any type of data. First, and most fundamentally, familiarity with data comes above all. The ins and the outs, the fluctuations and variations that come from sitting in it extensively. I personally have read thousands of opioid-related articles over the course of this project and often still do. There is a cycle to the data exploration and use, which echoes the model development cycle. Studying the data is critical at all stages. From reading articles, I was able to start to identify themes and questions that we could feed into different types of models. Then I needed to annotate, reading many, many, many articles and annotating them for whichever model we were currently developing. Knowing the variations and fluctuations helped to identify the border cases when evaluating the testing results and to support future tests. For a fun example, initially, our models would pick up articles about the mighty Morphin Power Rangers when looking for articles about morphine. Rare, yes, but totally out of scope and a good example of having to refine your models. While your own familiarity with the data is critical, even more so is collaborating with the content experts and the end users. Successful projects aren't about the computer science, it's about understanding the problem you're trying to solve. One of the biggest advantages we had, given the structure of an LDCP, was access to a wide range of potential end users serving on our core team, knowledge advisory group, and collaboration with a lived experience advisory group. All these individuals provided extensive subject matter expertise, which complemented the knowledge I gained from reading the articles. But more than that, we interfaced with them throughout the development process. For example, once I'd read several articles, I had a pretty good sense of what kind of articles there were, but to understand first what kind of articles would be helpful to end users, the scope of the tool, and then what kind of information from them was useful, the information to be extracted, we went to our broader group to get feedback and insights. Finally, we involved them in the design, testing, and interpreting stages of the data visualization. For example, it was our end users who ranked the different fields to extract, or who alerted us to potential biases in police confiscation data due to drug testing equipment. As a program evaluator with some experience in qualitative analysis, I found that approaching the data with that perspective, especially during the initial hypothesis and annotation phases, was valuable. During the hypothesis phase, I could use similar techniques to inductive qualitative analysis methods, such as constant comparative analysis, developing and changing themes as I reviewed more data. The development of accurate models requires consistent coding practice, a challenge where you have multiple annotators, certainly, but even a single person can drift in how they annotate. Here, taking approaches from coding and concepts like iterator reliability helped. For example, I developed codebooks or annotation guides with specific rules about how to annotate pieces. This slide is the guide for pruning articles as in or out of scope. Just briefly, we wanted to provide an example of a workflow for using the data from a technical perspective. First, you need a technical solution to actually annotate the data. In our case, we use both a formal tool called Prodigy, but also direct annotation in a database. Once you have a sufficient volume of examples, which can actually be a significant problem in the rare outcome scenario, you load the new examples and using techniques like match and active learning can pre-annotate the new examples to speed up the work required for human annotation. Believe me, it can get extraordinarily time-consuming and very tedious. You want any tools you can to speed this up. After the human corrects the pre-annotations, you store the gold annotations and continue to refine the intermediate model. Finally, once you have developed a full data set, you train the production model and evaluate it on unseen data, where again, more data needed. In our case, we needed at least 5 cycles of this process. The iteration of ideas for AI techniques is very much linked and intertwined with the understanding of the data phases. There are so many different models and techniques, and they are growing and changing literally every day. And then within each method, countless different parameters and options. You're going to have to try a lot of ideas and sometimes make radical changes in direction informed by how your model is performing, how the data is changing, what your end users are saying, and how the industry is changing. The the development process for AI projects is frequently going to be one where you lack time and often data. This results in a reality of non-ideal evaluation and trying to figure out how to make decisions when you are lacking the level of information you might want. I have no answers for you except to go into the process being prepared to make decisions with limited information and be ready to fail fast, otherwise known as throwing a bunch of ideas against the wall and seeing what sticks. And by seeing what sticks, I mean what is good enough. No solution will be perfect.
So in developing the data extraction component of the pipeline, we faced a critical choice between using task-specific in-house models and leveraging an end-to-end solution like OpenAI. We initially focused on building lightweight CPU-friendly models for specific tasks, such as extracting drug names and their appearance. These models were quick to train, energy efficient, and produce structured outputs. However, we quickly encountered limitations with more unique and emerging entities like nitazines. Annotating thousands of sentences to improve the generalizability uh, of these lightweight models was time consuming. And we, as Alison already kind of alluded to, we grew quite concerned about the volume of potential training data that was coming in real time. Alert messaging from PHUs, for example, is still quite rare, and the semantic content across alerts is fairly homogeneous and general in nature. To address these challenges, we started exploring large language models. These models are much better at handling diverse and unseen data. They can generalize well and have additional capacity for end-to-end entity disambiguation, linking, and normalization. We were also pleasantly surprised to see at how well they worked for location data. So these are all features that would require a battery of specialized components if we were to continue developing and building all of the models in-house ourselves. The ability of large language models to be exploited with in-context learning, and this is the example where you can prompt the model with examples, proved especially helpful for exploring and validating ideas early in our project. However, we quickly learned that they're not a panacea. They do have high operational costs. They do introduce dependency on an external API, and they are more difficult to fine tune, which can hinder precision in some applications. The most fundamental challenge, though, that we encountered was obtaining structured output. Even with carefully crafted prompts to produce structured formats like JSON, uh, large language models do have the tendency to return large and unstructured text blocks. This inconsistency in output presents a major barrier for integration as it complicates downstream processes reliant on standardized data formats. This limitation highlights the need for either supplemental processing layers that we would have to build or alternative approaches that force the model to return structured output. And this is something I'm going to talk about briefly next. So there are a number of tricks and tools, some of the main ones being grammars that you can use to try and force large language models to return structured output. I tried many of them. The more memorable and I would say really absurd was threatening the model to return JSON or we would take a life. And this is literally something that is suggested in some of the literature. Eventually, though, we landed on a better solution, and that would be a Python package called Instructor. To use Instructor, you define a data model that includes all the fields that you want in the output, along with their data types and some examples for few-shot learning if you have them. For instance, if you're extracting drug information, you might define a model with attributes like drug name, dosage, side effects, and all of these would be strings or a list of strings or integers. This data model or schema acts as a template that instructs the large language model on the exact format that it should follow. When the large language model is invoked, it generates a response conforming to this structure, filling in each field with the relevant information. Because the model is guided by a template, it's much more likely to return output that is clean and in a format that can be parsed later in stages of your pipeline. Instructor is also tightly coupled with a Python-based data validation library that some may be familiar with called Pydantic. And this integration allows you to extend your data model with validation logic that also includes thoughtful messages about the problem or the error that can be used to reprompt the large language model when errors are actually encountered. By combining OpenAI's flexibility with tools like Instructor, we felt that we mostly overcame the challenges of transforming unstructured text into structured data. But I should point out that the capabilities of local models, so local large language models like Llama 3.1, 3.2, and other proprietary models like ChatGPT are rapidly improving in this area, especially with the more recent advent of large language model tool use and agentic workflows. So overall, this approach enabled rapid prototyping while ensuring that the results remained somewhat accurate and well organized. Really, it did seem to be doing as good a job as our earlier in-house models for maintaining some of that structure. And it allowed us to exploit the advanced linguistic capabilities of large language models. And that really is what made creation of the A1's dashboard possible.
So we've now moved on to the production considerations, and we're going to start with data visualization, or whatever techniques you take to utilize the data you've collected via AI. It's important because it is the end product. Without it, all the other work doesn't come to fruition. In our experience, there are a lot of unique considerations to doing this work that come from using AI in the data pipeline. How you share the data is very much dependent on the structure and quality of it. In our project, we had two big considerations. Our data was primarily LLM extracted text, even if we didn't force a structured nature on it, and our original data source had its own limitations. Both of these resulted in an issue for how we were going to normalize the data, or not, and how that impacted how we were going to share the data. It was a very reflective process that we started early. How and what we wanted to share affected what data we extracted and how we organized it in the database. Alongside that came the need to be very clear about what the tool was and how AI was used during the pipeline. The documentation of the tool is extensive to be open about the limitations, and we included user testing and evaluation in the documentation to capture more of this. One of our big strategies was to design the dashboard from a trust but verify approach, ensuring in all places users had easy access back to the original article and so could verify the AI components for themselves.
So currently, right now, our validation process relies heavily on manual review, or what some folks in the industry like to call a vibes check, where we verify the output of OpenAI's model against the original source. Obviously, this approach works for small data volumes, although it's definitely not scalable, and issues like hallucinations, where plausible but incorrect data can still be injected into the output, can still arise. This is exactly really why we stress the trust but verify approach when you're using our tool right now. But to improve this process, we are exploring the use of local large language models for cross-validation, which could act as a secondary check, comparing extracted information with the source text to actually catch some of those errors. Additionally, we're considering implementing automated rule-based checks, such as checking for the existence of specific terms or phrases in the output with regular expressions in the source text to identify any failure modes in the pipeline. Looking forward, though, what we also want to consider around this evaluation piece is monitoring for model drift by tracking performance metrics like accuracy and precision, and comparing extraction results to those using new models, perhaps like GPT-4, and expanding some of our few shot prompting and validation strategies. This phase, though, will be time consuming, as it will require manually annotating a diverse and representative test set for this evaluation. But together, these improvements, local cross-validation, rule-based checks, and optimizing our prompting and validation logic, we do believe will result in a more scalable, robust validation system that ensures that the quality of A1's data quality is maintained throughout a project lifetime.
Just in the interest of time, we're just going to speed on to the next slide. Very quickly, summarize some of the biggest takeaways that we felt over the course of this project. We feel AI is a value add for tools in production, but there are upfront costs in time and complexity. Likewise, it's risky. You're not ever going to know that it's going to work when you start. We suggest not being married to the method. Don't focus on specific techniques or even limit yourself. The goal for public health is about using the right and most efficient tool. On a broader level, always work from the problem and include the end users. The majority of the project is not the machine learning component, but all the other things that have to go along with the project. And team dynamics and maturity of the team matter. Like with any other team, it goes through various phases. Alex and I had only worked briefly together when we started this project, and we learned a lot about each other and ourselves throughout it, but it also means the next project will be easier. And so we just wanted to thank you for listening before we get to questions. Please visit the web tool at the website on this slide. And there's ways to contact us both via our emails here and a contact form on the webpage. So now we can move on to questions.
Thank you, Allison and Alex, for sharing this information. Definitely a ton of work has to happen in the background and many challenges to overcome to make A1s possible or any AI-based application. We will now move on to the Q&A segment of the event to address some of the questions from the audience. So if you have any questions, please enter it in the Q&A pod. You'll see a button at the bottom of your Zoom windows. Please enter any questions you may have for the topic today if you had not had an opportunity to do so. There is a question. Maybe you can go back. There's a question about the link to the tool. You can type it in the chat or send it to me and I can paste it into the chat.
That is I can spell it out too, I suppose, kflaphi.ca. If you get there, you'll see the link to AONES.
kflaphi.ca. All right. Okay. There's a question on the chat from Mr. McGuire about risk. What is known about information that is put into open source AI? Do you have any experiences in thinking about that as you were working through A1s?
Yeah, that's a really good question. So we kind of struggled with this. Like there's like using a proprietary service, depending on like your license agreements with OpenAI, they can use some of that data to fine tune or retrain their model, like with the interactions that you're doing with the model. So that's one thing to consider, like when you're using a proprietary service, and there's a lot of like things with closed source there. I think the question is about about information being put into open source models. So this is something we were looking at. So there are open source models that are fairly, like at the start of this project, not easy to deploy, but becoming more easy to deploy. So things like Llama 3.1, Llama 3.2, these are models that are released by Meta or Facebook. And really what we think, and I have to explore this a little more, is that when you're deploying a model like that internally on your own infrastructure, like you don't just get the weights. There are some remote code that gets executed occasionally, but really just kind of going through and looking through what assets you're downloading and using to actually deploy that model internally. But I think the appeal for doing it locally is that you do actually just the data just stays on your local infrastructure and isn't sent to a third-party service. The trade-off there is that these models are we think much smaller. Like they do have like some models, if I'm remembering correctly, that are in the 400 billion parameter range for some of the open source models that you can download, but that requires like specialized infrastructure to run. But more of the smaller ones can be like around 8 billion parameters, so you could get it on a relatively common like consumer grade GPU, or maybe a few of those GPUs wired together. But yeah, there's lots of concerns around this about information and where it's being sent. I think if you're using a proprietary service, you want to make sure that you have enterprise agreements, security and privacy. They'll make attestations about where those models are running and what data is being used or reviewed by their staff. Like for example, with Microsoft, they will not review the output of some of the models and some of the guardrails there. But yeah, I don't know if I have a better answer than that. Just that, typically industry, the pitch has been that if you're using a local model, it's a little bit more secure. If that helps answer the question.
Thanks, Alex. There's a question in the chat about hallucinations. So it happens quite a bit with chatbots and LLMs. Is there a way, or have you considered a way for users to report any results that are inappropriate? So my understanding is provide feedback from your users if they're seeing anomalies in the
That is
outcome.
a fantastic idea. Right now, we don't have a way. when I have time, I'm still doing sort of reviews and trying to, certainly for the ones that we care the highest amount about, which are the alerts, trying to continue to annotate data and remove ones that are not alerts so that we can continue to keep a really good training data set. But right now, we don't have a way for people to support us in that, though it would be really amazing if we can. There are lots of technical difficulties. We discovered one of our biggest technical difficulties during this project in the annotation was that we hoped that more people would be able to annotate, but it's a very hard to distribute over multiple networks. So it's no easy answers to that.
With regards to like hallucination, I think like some of this validation logic in using some of these libraries like Instructor can help with that, but really like maybe doing like reprompting and then having another model in the loop to kind of verify whether or not some of that content matches, like a secondary model that isn't the same one that you're doing the inference with, maybe a solution. But yeah, this is a common problem across all these big projects, and really like it's not solved yet. So like there are other tricks, like you can use retrieval augmented generation by putting more examples in the prompt. So like for in context learning, can help, but yeah, it's not completely solved. I also see, I'm just kind of jumping over, but I do see a question about when we were training our local models and the cycles that we went through and how we decided when to stop. And really, I don't have a very like satisfactory answer to that, other than that we grew panicked. And this was me around Christmas time of last year, recognizing that we didn't have, endless time to work on this project and we had to have some output, that we just were not getting enough examples, like unique examples. Like we were getting very good at like predicting the word fentanyl in some of these articles. And it was like, well, do we need a model for that? Because like we could probably just have a rule-based method to kind of do that really accurately. But typically the tools I use, Spacey is a Python package for machine learning, natural language processing. They also have some really great annotation tooling called Prodigy. And they can actually generate training curves, and you can look at like the amount of improvement at certain parts of your training pipeline, and to give you some indication as to whether more data needs to be collected for generalization. But I think really here it's just kind of getting a feel for it. I think we really just recognized there wasn't a lot of unique data coming in and that we need to explore some other ideas. And this was sort of when the large language model stuff was exploding on the scene. So we decided to give it a try. It wasn't exciting at first because we were getting a lot of text, like we get good answers, but like a huge hunk of text back. And, the murmurings among the team were like, well, that's fun, but it doesn't really actually solve the problem. We're not going to be able to build a dashboard with that. So what are we going to do? So that's kind of what pushed us along. So I hope that's somewhat satisfactory answer, but yeah, it's really just kind of getting a feel for it, and then just recognizing when, you're not really getting enough data to really generalize.
Just to add to that question, Alex, if you don't mind, was cost ever, uh, you know, a metric to, pause training? If you run out of compute cycles or credits, was that ever a
Yeah.
factor at all?
Fortunately not here in this case, because we did actually spec out the development of this around deploying locally, and still have intention of deploying other parts of the component locally. So we did have enough GPU capacity to run. So the types of models like for doing like entity extraction like really well, are not necessarily like huge. They're not large language models. They're like what we like, they're just language models, like smaller, like supervised models that actually can train quite quickly if you have GPU infrastructure. It does really depend on the size of the data that you're sending. Like if you're trying to, classify in one go, like a large body of text, or if you have multiple components that are trying to essentially like do that disambiguation. So one of the problems we had was, yes, we're good at identifying like some of these core concepts, like the drug appearance or the name, but how do we link those? So that requires another method. So as you kind of get more complex about like what you have to extract, and that structure, it becomes more GPU and compute intensive. Also depends on like the underlying models that you're trying, and architecture you're trying to do that with, whether you're using transformer models or convolutional neural networks, like different things like that. So it's just kind of playing around with it. But yeah, we were fortunate to be able to experiment quickly with that. It was really not having um, a lot of examples and recognizing that this is probably not going to generalize the way we want, because we wanted to be able to detect new substances without having to train a lot of like data. We didn't have enough examples. So like, how do you detect nitazines if it's never seen nitazines before, kind of thing. So
There's a additional question about training. If the AI model, and I'll paraphrase, if the AI model is basically not performing as expected, is it able to does it provide you feedback on future input data? If if it's not been trained properly because of bad data, is it going to be providing you feedback?
I think, yeah, no, not really. Models like they garbage in, garbage out, right? So you're still going to have problems with that. I think what you may want to look at in that scenario is like libraries like Clean Lab, different things to look at, the quality of your annotations first going in, like the diversity. Like you don't want to be testing on examples that are exactly the same as the stuff you're training on. So I think more data quality type checks before are going to be more important. The model is just going to happily train and memorize potentially things and spit out crap if you put crap in, if that makes sense.
Thank you. There's a question that aligns with one of my questions, which is the resources involved, as well as how long did this whole thing take?
So in this case, because it was an LDCP funded project, we had very strict timelines. PHO was very generous to us to sort of work with us to slightly extend those timelines, because this was an incredible amount of work in a very short period of time. We basically started from scratch in April and had to have something to show by March, though, much of the documentation and knowledge exchange didn't happen until after that. But the majority of the work had to happen in 8 months. And as we've been over in this presentation, a lot of those first few months, we weren't really actively doing the machine learning component until late November or early December, because it took all those months to get the computer, to get it set up, to get all the policies in place and those sorts of things. So most of the work really of the AI component really went from late November through March, which was very busy. And mostly there were just two of us, Alex and myself, with significant support from a few other colleagues here, including a data integration specialist who was integral to help us get many of the backend features up. And then, of course, we had the support from scoping and those sorts of things of a much larger group, but the ins and outs of doing the work was just a handful of people.
And that's kind of like the take home message here, is that like we did kind of underestimate the amount of like infrastructure we would need to set up to kind of get this to run. Like the machine learning aspect is only really one little piece of it. The rest of it was the most time consuming part, like setting up things to be secure and like to save the data, to build pipelines, all that stuff took much longer.
All right. Well, we're 2 minutes to the hour, and thanks so much for all the questions. I know there are still many questions that we weren't able to answer. As we wrapped up the session, I'd like to thank again Allison and Alex for presenting. And thank you to everyone who joined today's webinar. You can expect to receive a brief and anonymous PHO Rounds survey for the session, and please try to complete this to help improve our programming. Lastly, if you want to access past PHO presentations and to look at upcoming sessions, please visit the PHO website and head to Education and Events and click on Presentations. Thanks again to everyone for joining, and have a wonderful day.